Shall we start? Hello, everybody. Looks like beer what you have here, but it's not, isn't it? All right, today we are going to do something revolutionary. I'm going to show pictures. This is the first picture. You know this website, I'm sure. First of all, I wanted to make you aware of this Jupyter notebook here. So if you click here, it will offer to download this Jupyter notebook. Now, if you then run it, you see something like this. Probably a little bit too small for you to read this, but it's not so important. So this is a collection of cells in this Jupyter notebook, so pieces of Python code, with which you can play a little bit with all these functions, cosmological models, and so on that we spoke about. I just wanted to make you aware of this, so that you maybe can play with that. It defines a class for a cosmological model first, then a class for the power spectrum within that cosmological model. That, of course, contains all these correlation functions and so on. And then it does several calculations that you partly encountered during the tutorial groups and so on. So maybe, if you like, have a look. All right. So that's what I wanted to show you. Another thing is that I wanted to show you a few pictures concerning, first of all, perturbation theory. I will need this as an introduction for today's lecture. This is from a paper that our master student Shafak Celik and our PhD student Christoph Pixius recently published. And it shows you the first two orders of perturbation theory. So what you see here is the small scale part of the linearly involved power spectrum. That's boring, right? That's just initial conditions scaled up by the square of the scale of the growth factor. This is just there for comparison. Now you see, this is the first order, this curve here. And it does something very characteristic. There is a dashed part of the curve. This means that the corresponding section of the curve is negative. And of course, since this is a double logarithmic plot, you can't easily show the negative part, so we show the negative part in dashed lines. So this means that you see how power is removed from larger scales and added to smaller scales. And of course, you expect things like that, right? Because gravity is attractive, and you expect perturbations to flow, so to speak, from large to small scales just because they're being contracted by gravity. And that's what you see here. And each of these orders of perturbation theory is characterized by a scale below which you reduce power and above which you enhance power. And we call this mode coupling, because larger scale modes are coupled to smaller scale modes, and the power that was previously in larger scale modes is flowing to smaller scale modes. And typically, this kind of mode coupling is expressed by convolution terms in the perturbation theory. This is exactly like in quantum field theory. You have loop diagrams, quantum field theory. These loop diagrams correspond to convolutions, and they do exactly this thing. Right? They couple modes of different wave number to each other. So that's one interesting thing. The next interesting thing is that this crossover scale here, where reduction of power switches over to enhancement of power, this depends on the order of perturbation theory. And then something really troublesome happens. Right? The amplitude of the first order term is approximately equal to the amplitude of the second order term. This is something we don't like, because usually you would expect the second order to be much smaller than the first order, and this is not the case. And this is bad. And I told you before, right? Perturbation theory is bad for your health. And here is one reason why. The other reason you already saw, right? It leads to an enormous number of terms that you will all have to evaluate, or the computer has to evaluate that. And this costs a lot of electric energy, and electric energy has become very expensive, and so on. Now, if you add these terms, then you get up to second order perturbation contributions to the nonlinear power spectrum. And here you see what happens. This is now the red curve here. The green curve is the reference. This is the linearly evolved spectrum. The linear and the sum of the corrections added together is the dashed dotted blue curve here. And the crosses show what numerical simulations find, which are, of course, fully nonlinear. You see that even after second order, there's still a huge gap to bridge. And as I told you 2 weeks ago, Christoph Pixius is now up to, I think, 8th order, and there's still a gap. I'm not sure what to do with it. Nonetheless, this shows you what perturbation theory does. You can perfectly calculate these terms, and the convergence seems to be very slow. If it converges, which you don't know. Okay, so today, for this reason, we are going to do something completely different. But yeah, that's the right reaction. Before we do that, let me come back to what we did last time. And last time we studied the asymptotic behavior of the nonlinear but free power spectrum. Why is this interesting? Because, of course, if we study nonlinear structure formation, we are interested in the limit of very large wave numbers. That's where the action is, right? That's what we want to understand. What we want to understand. And I showed you, after some detour into the mathematics of Laplace and Fourier Laplace type integrals, that one can prove that the asymptotic tail nonlinear free power spectrum has to fall off like k to the minus 3, where the 3 is set by the number of spatial dimensions and nothing else. And this means that this kind of behavior is universal. And it doesn't even depend on cosmological background, does not depend on the initial power spectrum of dark matter, and so on. It's a very important result. What does it tell you? If you do not look at the power spectrum itself, but at a quantity that we call the power, which is wave number cubed times the power spectrum, then you multiply the characteristic squared amplitude of the density fluctuations by the number of the density fluctuations that you have available. This is why it's called the total power. And then you see that if you do this operation, then the power spectrum times k cubed, the power becomes completely flat. In other words, the amplitude of structures times the number of structures becomes completely scale independent. This is extremely important for our understanding of nonlinear cosmic density fluctuation. Now, of course, this was the free power spectrum, and who knows what happens if you switch on interaction. So I wanted today to give a brief look into the current current status of our work on taking particle interactions into account. And then you can see what you think of that. But before we start with that, do you have any questions on what we did so far? Not the case. Then let's have a look at these other things. So today I wanted to speak about what we call the mean field approximation. And the mean field approximation is, of course, no invention by us, but it's very well known in other fields. For example, in solid state physics and statistical physics, and so on. What does it mean? So far we have treated the interaction between particles such that we take every pairwise gravitational interaction between any pair of particles into account. Well, this is certainly the best thing you can do. However, if you have a very large number of particles, then the whole collection of particles becomes more or less smooth. Then the fluctuations in the force that any particle experiences, caused by the matter density field being decomposed into particles, become smaller and smaller. Let's suppose you have very few interacting particles, and you pick out one after the other of these particles, and you ask, what force does this particular particle experience? Then, if the number of particles interacting with that particular particle is small, the fluctuations in the force will be large. If you add more and more particles, fluctuations will become smaller. Now, there's a problem with gravity, because gravity falls off like 1 over r squared in gravitational force. But the number of gravitating particles in a shell of radius r grows like a thin shell of radius r, grows like the square of that radius. And this means that every shell at a certain distance adds particles, and the number of and the fluctuations in the gravitational force goes down very slowly because of the 1 over r squared gravitational force law. But due to our reference trajectories, which we have chosen to be of Soldovich type, the gravitational force relative to these trajectories does not fall off like 1 over r squared, but steeper. Remember, because we took the large-scale part of gravity already into account when we constructed the fiducial trajectories, our reference trajectories, this means that the large-scale part of the gravitational interaction needs to be subtracted. And therefore, we will see this more clearly later today. Therefore, the gravitational potential, the gravitational force, relative to our particular reference trajectories, falls off more steeply. So this means we do not have this problem of infinitely growing fluctuations in the gravitational force. We have very many particles, right, because we must assume that dark matter, for example, is composed of elementary particles whose mass is extremely small, of which we must have very many if we average over cosmological distances. So we have a very large number of particles, and we do have a short range interaction law. These must be ideal conditions for an approach that is often applied in solid state physics, the mean field approach, where you say, all right, I don't care of the fluctuation. I just take the mean force between a smoothed out density field and individual particles into account. This should be a way to avoid perturbation theory. And you saw the problems of perturbation theory very clearly, I think. But of course, another problem is now how to construct. You're smiling, you know of this problem. Anybody here many people here in the room know of this problem. Anyway, yeah. So often in mean field approaches, the definition of what you call a mean field will not be very clear. I will show you one example which is particularly simple today, and one can easily make them more complicated. But I wanted to illustrate the idea, and I wanted to show you one particular result that we have obtained with this kind of mean field approximation. I'm not claiming that this is in any way final. There's a lot of work still to be done. But of course, I wanted to give you an idea of that. All right. How do we do that? Let's start with the generating functional. With what else? Right? It's the mean field app. You can download this from the Google Store. So I want to write down the complete generating functional, that is, including particle interactions, but already after having applied a certain number of density operators. And to keep it simple, I want to assume that I have two density operators applied, so I'm looking at a power spectrum. So the L, the shift tensor L here, contains two contributions. We'll see about that. And as you know, I can write this generating functional as an integral over initial conditions. Now, scalar product of L with x bar, and x bar is the trajectory of the particles, the bundle of particle trajectories, taking particle interactions into account. All right, that's our starting point. That's exact. There's nothing to dispute about this. But let's see. L is what? Now, if I have two density operators applied, there's a wave vector k1. There's this vector 1, 0 that picks out the q component of the shift, so the position component of the shift tensor. Then I have a delta distribution that singles out the point in time where I want this density operator to act. And now I need to say which particles are shifted in this way. Since I have two density operators applied, there must be two particles. Now, usually I should have k1 times e1, vector e1, plus k2 times vector e2, but k2 is minus k1 because they need to add up to 0. So I can just write this e1 minus e2, and then we have our shift tensor complete. All right. Are you fine with this? Okay. Now the x bar consists of a free part, which you know and like and so on, but which I don't care today for this. Rather, I'm looking at something else, which is the interaction or interacting part of the trajectories. This is where the action is, right? This is where the forces are. Now, what is this y bar? Which propagator do we need here? You can use both, right? The Hamiltonian propagator or the Seldovich propagator, but the expression for the force is much easier if we take the Hamiltonian propagator. Okay. And now we have forces acting on particle J, and they appear in the momentum component here because they change the momentum of the particles, according to P dot is F. And this happens for all the particles. And of course, later we need an expression for the force acting on particle J, but okay. All right, now we combine these two. Remember the Hamiltonian propagator looks like this. One small g and small g. You remember? What's this thing? All right. Now, as you see, if I multiply this propagator here with this force term, I will get a two-component vector which contains GH times F in the first component. And I don't care about the second component because this one picks out only the first component. So this means that the scalar product that I need to evaluate, now restricted to the interacting part y bar, is simply minus k1. This delta function here sets this upper integration limit to t1. So I have this expression here, and now I get two Kronecker delta from the scalar product of these two unit vectors here with this one. So I get delta 1j minus delta 2j. And that's the complete scalar product between these, between the shift tensor and the interacting part of the trajectory. Okay, so the only thing we need to know is this force difference here. Propagated forward with the GH, but okay. So that's what we need to evaluate. And I think one thing is clear. If we had a truly random field and we would take the difference in the forces acting on two arbitrary particles, and we would average over that, it would be 0. So can we stop here? Of course not. Of course not, right? Because the particles, first of all, are correlated with each other. So the two positions that I pick out for the particular particles that I'm looking at will not be random. And of course, they are not random with respect to the surrounding matter distribution either. So some part of the force must remain. And we are looking for that. Because, and this is the crucial step now. Suppose I can replace this here by an average. However I form that. That will depend only on the positions of these two particles, because we still have a homogeneous situation. So it can only depend on the difference of positions. Then it's the final positions of the particles. But this integral here goes over all the initial positions. And then I can pull the average force out of this integral. Then I can do the following thing. Then I can write the free part only with something in front here. Which would be a suitably averaged interaction term and not an operator. That's the idea, right? So instead of summing over all the particles as we would have to do for an exact expression, we try to find a suitable average for this force difference acting on the two trajectories that we are pursuing. And then once we have replaced this force difference by its average, then we can pull it out of the integral and we are happy. Then it will be sufficient to calculate the free generating functional. And how we do that, you know. Right? We factorize it and then so on and so forth. All right. So what would be a suitable average of this? Okay. If I look at any particular particle with the index j, it's located at qj, I know that the force on this particle is given by density operator representing this particle times the velocity, times the potential gradient acting between positions q and y times the density at position y, and here I need to integrate over q and y. You remember that, do you? That just says I take the force between any 2 points and I weigh this force with the densities at the respective position. But that's nice because now if I take an average, tentatively, I need to average this. And now you see, of course, the potential gradient itself is not a random quantity. So that's unaffected by the average. What remains is just the average over this product of densities here. So what remains is this expression here. But you know what that is? Right? This is just given by the correlation function of these densities. We are in a homogeneous random field. So this expression can only depend on the difference of coordinates. The result for this average here is this is n bar squared 1 plus the correlation function as a function of q minus y. By definition of the correlation function. And if the particles would not be correlated, we would just have the n bar square here. And then if you integrate over, if you integrate this over here, then you integrate over a random field, which has no preferred direction. A vector, the vector nabla q, nabla v, and this will be 0. But in a homogeneous random field, there will be no average force. And every non-vanishing force contribution that you may have must be due to correlations between particles. Okay, now, since I'm cross-correlating here the complete density field with the density field for a single particle only, I need to correct this by dividing by the number of particles here. All right, now there's a constant term. If I integrate this over, it will vanish. So I can leave it out. The correlation function depends on q minus y only. So I'm going to substitute the y integration by an integration over q minus y. Then nothing in the integral will depend on q. So if I integrate over q, I will just get a factor of v, the volume. Volume divided by n is the inverse density. Right, so then I can write this as n bar. The rest is gone. Now, integral over q minus y. I'm renaming this variable here. Right? Gradient v of q times psi of q. Okay. That would be the expression here. Now comes a dubious step. A dubious but simple step. And this is not rigorous. I'm not claiming this to be rigorous, but I'm suggesting that this gives the idea that we should replace the potential gradient nabla v by the potential gradient weighed with a correlation function. Yeah. Yes, you're right. But let me write it this way. All right. This suggests to replace nabla v by nabla v times psi. This is not strict. This is intuitively plausible because, as you know, the correlation function is the conditional probability for finding a certain pair of particles. In other words, I'm replacing the potential gradient by the potential gradient times the probability to find the two particles that I want to apply this potential gradient to. All right. One can interpret this differently, but this is what I'm now doing. I'm going to use this as a new potential gradient. Okay? So far, so good. Let me erase my traces. Now, with this in mind, let's have a look at a quantity like this, which I want to average over. And now I'm doing the following. I'm representing this in Fourier space. In other words, I will have a k integral. Then I need to express the I need to express the gradients here also by their Fourier modes. So the gradient is just an ik. Then I will have the Fourier transform of the potential. And for the potential, we'll insert the probability weight potential as upstairs. All right. Then I need to take account of the Fourier phases here. And this is ak times q1 minus y, where y has the same meaning as above, minus e to the ik times q2 minus y. All right. Now I need to say over which points y I want to integrate. Because in order to get this average force term, I need to integrate over y as well. And now comes another thing that you might dispute. Right? I'm going to insert delta functions at the positions of the particles themselves. In other words, I'm looking at the net force that remains because the two particles that I'm considering are correlated to each other. Now, where's the mean field approximation? The mean field approximation says I'm averaging the force on particle 1 by a mean field at the position of particle 2. And then I'm exchanging the role of these two particles. And you know that by Newton's third law, this just will give us a factor of 2 for the force. All right, now I'm going to represent these delta functions also in Fourier space. I'm going to write e to the I k prime times q1 minus y plus e to the I k prime times q2 minus y. Okay, in other words, I'm evaluating this mean force term at the positions of the two particles. Okay. Now what's going to happen? I also need to integrate over y, right, according to our prescription of the interaction term. Okay, now let me order terms a bit differently. I have the two k-space integrals here. I, k, phi tilde. Now you see, from each of these factors, I can pick out an exponential of ik minus y times e to the power of ik prime minus y. I'm collecting all of these at the end. So this leaves e to the ik q1 minus e to the ik q2 e to the ik prime times q1 e to the ik prime times q2. And now these are the only quantities that still depend on y. E to the I k plus k prime times y with a minus sign. All right. This gives me a delta function k plus k prime. This means that when I now integrate over k prime, it will replace k prime by minus k. In other words, I can write this as a single integral here of I k prime times phi tilde. This is a phi tilde of k, of course. Sorry, k times phi tilde of k. E to the I k q1 minus e to the I k q2 e to the minus I k times q1 plus e to the minus I k times q2. Okay, and now you can play games, of course. This one and that one together give plus 1. This one and that one together give minus 1. And all the cross terms look alike. So I only need to take account of the mixed product. And I'm left with ik phi tilde of k e to the I k times q1 minus q2 minus e to the I k q2 minus q1. That's what's left. But the two integrals are equal. Look, if I take this, where I have q2 minus q1 in the order as I like them, and then compare what happens in the first term. There's just a minus sign in the phase. But this I can compensate if I substitute k minus k for k. This will not change the complete k-space integration, of course. It will change the sign of this vector k here. So then I will have a minus sign in both. So this is just minus 2 times I. Now an integral over k phi tilde of k e to the I k q2 minus q1. That's it. So now I have an average of the potential gradient difference at positions q1 and q2. And you see that if I want to express this average gradient difference in Fourier space, and I do want to do this because I want to look at power spectra, not at correlation functions, then, of course, I only need the Fourier transform of this quantity here, which will, of course, just give me a minus 2 times I times k times phi tilde. All right. So this is now the potential gradient that we have to look at. All right. So this average, taken in Fourier space, it was in configuration space before, must just be minus 2i. 2 is just Newton's third law. Right? Sorry, it's badly enumerated. The 2 should be for Newton's second law. I can't possibly write down 3 here. K times phi tilde of k. Okay? This is one result, right? That's a result of this particular form of averaging. And now I take into account that we wanted to replace the potential gradient by the potential gradient times the correlation function. Okay? Now this was a product in configuration space. This will be a convolution in Fourier space. So, in other words, this Fourier transform of the potential gradient must be a convolution, so some integral over another wave number k prime, of the Fourier transform of the potential that we had before, taken at k minus k prime, times the Fourier transform of the correlation function, which is the power spectrum. All right? The individual steps are quite easy. Right? I'm averaging over the force difference. I'm evaluating this average between the two particles. I'm arriving at this formula over there, like this formula here. Where the factor of 2 just reminds of the fact that the total force between the particles is the sum of the forces on the individual particles. Then I'm making this substitution here. I replace the potential gradient by the potential gradient weight by the probability of finding these two particles. This gives me this result here. All right, and now I can continue. All right, so what have we got so far? I need to evaluate this at some wave number k. All right. We had a factor of minus k1 here from the shift tensor. No. Confuse this. I wanted to return to the original expression that we had for the interaction term. Let me write this down again. All right. So we had that this expression here was minus k1 times the integral from 0 to t propagator times this thing, right? Okay. Now we have studied the potential difference in potential gradient. But remember, with respect to the Seldovich fiducial trajectory, Seldovich reference trajectories, the force term was not just the potential gradient, but it was m times the potential gradient here, and m was the time-dependent mass. So we need to take this into account later. But you see that if I want to have the average of the force term, I can take the average of the potential gradients. And the average of the potential gradients, as we saw down here, we need this factor of m, and now we have the convolution. This k minus k prime, p delta of k prime. And now, since we are aiming at evaluating the average interaction term at a wave number k1, it's set by the density operators, I need to insert k1 over here. Okay. So far, so good. Do you have any questions so far? Yeah. It's the time-dependent mass, yeah. Do you want a break? I should say that I need to be at the rectorate today at 4 p.m. So I should run away at 10 to 4 at the latest. Short break, no break. Short break, very short break. Yeah, let's restart in 5 minutes, okay? Time to restart. All right. So this is our recipe so far, but I have already replaced the scalar product that we had before by an average of the scalar product, which now contains the average of the potential gradient, and it contains this factor m to convert the potential gradient to a force. So far, so good. But now we have to think of the potential, right? Yeah? Yeah, we'll get to that now. So now I need to say a little bit more about what exactly the potential really looks like. And we said before that somehow the large scale part must be gone, but the way how we make it disappear and what the actual form, in fact, in Fourier space of this potential is going to be has not been clarified yet. Remember, we had that the potential phi is given by the Poisson equation with some amplitude a phi, which depends on time, and non-linear density contrast only. Okay. Now I'm going to distinguish between the potential phi and the potential caused by a single particle, which is little v. And this will be expressed by this equation here. The potential caused by all the particles together will be a convolution of the density contrast of these particles with a one particle potential v. Okay? Think of this delta here as being composed of individual delta functions. Then you would just get a sum of the potentials of the individual particles. Okay. Now, of course, if I see a convolution, I immediately try to escape into Fourier space. In Fourier space, the nabla squared operator here will be a minus k squared. And I will have the Fourier transform of the potential phi, which will be the Fourier transform of this convolution, which is a product of the Fourier transform factors. So this will be delta tilde times v tilde. All right. Notice that this is the complete density contrast, right? Not just the nonlinear part. Now I'm going to write the nonlinear part as the complete density contrast minus the linear part. Okay. That's beautiful. It contains a lot that we don't know. I don't know delta. I have an idea what delta tilde is. The linear delta. Okay. Good. Now, I'm taking this equation, I'm multiplying once with delta tilde and once with delta linear tilde. This gives me minus k squared delta tilde squared v tilde phi delta tilde squared minus a cross term. And the other becomes k squared times the cross term times v tilde. And on the other side, the cross term minus the linear squared. I'm doing this for the following reason. I know what the average of delta tilde square is. That's just the power spectrum. I know what the average of delta tilde linear squared is. This linear power spectrum. I do not know what the average over the cross term is. I want to get rid of this. This is why I have to eliminate it now. All right. In this equation, it only appears once, so I'm picking out this one. And as you see, this gives me that the cross term is this term here. Minus this one. I hope I didn't do anything wrong. Should be okay, isn't it? Can't be okay. All right. I'm dividing by a phi. I'm changing sign. And I have to add delta tilde squared. Do you agree? Okay. Now I can insert this into here and eliminate that. This will give me a quadratic equation in V tilde. Because here I will have to replace the delta tilde times delta tilde linear by this expression, which will give me a term quadratic in V. Here will be a linear term in V. So it's a mixed quadratic equation. I can easily solve that. And without doing this, you find that the Fourier transform of the two particle, or the potential of a single particle, is going to be minus a phi divided by k squared. That's the inverse Laplacian here that we have to apply. In the Newtonian case, we would be done. But now we have square root of p linear Okay, I'm getting this factor here. And I forgot to multiply with the mean particle density over here, which gives a 1 over mean particle density everywhere here, and also here. And this will cancel the mean particle number density that we had in the force factor. Okay, but the main thing is the following. Now suppose we are at scales where nonlinear structure formation has not happened yet. There, the nonlinear power spectrum equals the linear power spectrum. There is 1 minus 1 then, so then the potential, the Fourier transform of the potential becomes 0. This means that on large scales where nonlinear structure formation has not happened yet, the potential is just gone. On small scales, where the nonlinear power spectrum is very much larger than the linear power spectrum, this goes to 0, and the Newtonian potential is going to be reinstalled. Of course, the exact form of this expression here could be calculated in hindsight, but if you take numerical simulations as a guidance, you find that this factor here can be approximated by, can you read this, k squared divided by k squared plus k0 squared. This has exactly the behavior we need, right? If you drive k to very large numbers, very much larger than k0, then this goes to 1. If you drive k to 0, then it goes to 0. And this is in fact, very good fit to numerical simulation. I do not have a better justification yet. But, as you see, if you insert this, you get the very remarkable form, a phi divided by n bar k squared plus k0 squared. That's the Fourier transform of a Yukawa potential. Right? So this means that we can express the fact that our potential should become short range by including a Yukawa term as if the graviton had a mass. All right, this is what I wanted to show you. Right? This is now what we will have to insert, this form here, what we will now have to insert into our convolution term. Okay? So now we have the next step here. This potential here that we will have to insert over here has the form there should be a factor of n bar here, which is ready to be cancelled by this one. Right? This is the form of the potential we need. And remember, this is an approximation, but it seems to be a very good approximation. It does exactly what we want, right? It cancels the large-scale part of the gravitational interaction, and it leaves the small-scale part. Okay. Good. Now we have all the ingredients together. Now we can just carry out the calculation. Yes. You could get this from KFT itself. Right? You start with a guess. You calculate the first nonlinear power spectrum. This nonlinear power spectrum by this square root here gives you next iteration of K0 and so on and so forth. This is the whole. Okay. Nonetheless, now we have to carry out an integral like this. It's the convolution integral between the potential gradient. So this is k minus k prime times the Fourier transform of the potential itself. So this is k minus k prime squared plus k0 squared. So now in this formula we are here. Now I have to integrate over p delta of k. And of course I would have to multiply this with a phi, with the potential amplitude, and so on. But this is the integral we now have to solve. Okay, now this is an integral over the complete k prime free space. But p delta of k prime depends only on the absolute value of k prime and not on its direction. The only terms that depend on direction are stuck in here. So here I can do the following thing. I can integrate over k prime squared dk prime divided by 2 pi to the power of 3. That's part of our definition of this Fourier back transform here. This goes from 0 to infinity. Then I will have to integrate over d phi from 0 to 2 pi. Then I will have to integrate over the direction cosine. And now, since k prime is varying all over 3 space, but k is fixed, I'm introducing k as the polar axis, and then mu is the angle between k prime and k. But then I know that there must be rotational symmetry about k. So this means that all the phi integrations, will return 2 pi. Right? What I can do is so I'm keeping k fixed. I'm integrating k prime all over the place. The integrand does not depend on the azimuthal angle that k prime can describe with respect to k. So there's no dependence on phi in here. So oh, there is a dependence on phi. Here is k. Here's k prime. Now, I'm going to decompose k prime into a component parallel to k, this one, and a component perpendicular to k. And this component, the contribution from this component will average out. So I can replace this numerator here by this expression. Look, everything that remains of the k prime vector is the component of k prime in k direction. And this is given by this expression here. Here I get k squared plus k prime squared minus k prime 2 times cosine angle between, so times mu times p delta of k prime. All right, that's it. Plus k0 squared. Okay. Now, you see that for the remainder, there is no phi dependence anymore. So this just gives me a factor of 2 pi. Then I can pull the vector k out front. Then I'm going to substitute k prime over k by a variable kappa. Then I'm going to pull k squared out from here. And then I get, first of all, a simple integral in mu that I can directly carry out. Now, without doing that, this gives me an integral from 0 to infinity I pull k square out, I'm going to replace k prime by kappa times k. So this gives me a factor of k cubed. This gives me another vector k here. So this will be vector k times absolute value of k. And later, we will have to multiply by another vector k, so that the total thing will go like k cubed. It will go like k cubed. All right. Then I have a kernel function which I call kappa, and which is j, which is the mu integral of this thing. I'm going to show you what it looks like. I'm not going to do the calculation, but the calculation is not difficult. And this will depend on kappa, of course, the y prime, the k prime of k, and it will depend on k0, or instead of k0, I'm also introducing k0 divided by k, so this will then be a kappa 0. That's a unique kernel function, we'll see about that. And then I will have to integrate over p delta of k times kappa and kappa squared d kappa. Yes. Now this is a kernel function times the power spectrum. That's a moment of the power spectrum. I'm calling this moment just sigma j. And the sigma j will depend on k. And it's just an integral over the power spectrum, weighed by this function here. Okay. Now I can pull things together, of course. Now I have a very simple expression for this convolution. So then I have an expression for the average difference in the potential gradient. And I can insert this here. And I'm getting a factor of, oh dear, I'm getting a factor of k, a vector of k in addition. Here I have to replace k by k1. And then I get for the average scalar product of the interacting particle trajectories with shift tensor evaluated at k1, I get k squared, k1 squared times k1 is k1 cubed. Then I have all these constants here, a phi. I must have lost the factor of I somewhere. Doesn't matter now. Sigma j. Okay, k1. And that's it. That is a very simple expression. Okay, since a phi depends on time, I still have to integrate over time. In this way, and the variable mass goes into that, and so on and so forth. Right? But the principle is that you just take the moment of the power spectrum, and the rest is just given by this expression. All right, now let me show you what that looks like. So first of all, this is this function J of kappa and kappa 0. In other words, that's the result of the mu integration of that integral that we had before. And you see, all right, if you drive kappa 0 to 0, then you reinstall the Newtonian potential. And depending on where you fix kappa 0, the amplitude goes down. On long scale, for large kappa, it develops just a k to the minus 2 tail, and has this characteristic form. All right, now you can also easily switch between the Newtonian case and the Yukawa case, and it will just lower this amplitude here. All right, now this is the mean field interaction term. And this becomes k independent. And this is because the, okay. It's not easy to see, but it does, as you see, it becomes k independent over here. Yeah. This is just the exponent of this prefactor. You see, it's very small and on small wave numbers, so you don't see it over here. It becomes large for large wave numbers, and it becomes scale independent. And if this is true, and if our mean field approximation is trustable, then this means that our asymptotic result for the free power spectrum will also be valid for the interacting power spectrum, right? Because you multiply it by a factor that is k independent. You raise its amplitude, but the asymptotic tail should remain the same. Very important if true. Now this is the power spectrum. There's a yellow curve underneath, which is the result from numerical simulation. The dashed curve, as before, is the linearly evolved power spectrum as a reference. And of course, on large scales, small wave numbers, the power spectra agree. And I'm showing only the small scale part here. And then you see the agreement between the analytic result, according to this type of mean field approximation, and the numerical result is extremely good. I have not mentioned that we have adapted parameters in order to make this fit work. But the shape of the nonlinear power spectrum is extremely well represented here. If you compare this to results from perturbation theory, and it's clear that if that works, right, then this is the much more advantageous approach. It should be really good because we have a very large number of particles and a short-range interaction. And as you asked before, Christian, and I said, of course, the case 0 is a free parameter here. Now we can adapt this to the result of numerical simulations, or you can calculate it directly from kinetic field theory in a kind of consistency relation. This is all ongoing work, but I wanted to show you this. And this power spectrum here is filling us with a lot of optimism. If you get it to this accuracy here, if you plotted the accuracy, the accuracy would be at the percent level up to k equals 10. Then there must be something right to the mean field approximation. Okay, this is what I wanted to show you today, right? There must be a way to replace the gravitational interaction in the mean field approach. What I showed you is a crude first way of estimating what could happen. the result of this estimation looks extremely good and very encouraging. But now, of course, we need to refine this. Now, how could you refine this? Well, there are many possibilities. Just wanted to sketch one of them. Let me show you what we are currently trying to do. Somehow we need to average this term. Right? We have a potential gradient difference evaluated at two correlated particle positions. Their correlations we've taken into account in the approach that I've shown you. But there is, of course, also a correlation of each of these with the density fluctuation itself. And this is a correlation we have not taken into account yet. So rather than doing what we did so far, we should do the following thing here. I'm calling the density contrast here, density contrast at the position 3, delta 3. And now we need a probability distribution for finding a particle at Q1, another one at Q2, and a density contrast delta 3. And this probability distribution can be derived in several approximations. It leads to a much more complicated term, of course, which you can then cook down, but this must be a way to improve the mean field approximation. This, of course, is a 3-point correlation. So far, we have only taken 2-point correlations into account. But any 3-point correlation can be decomposed into pairs of 2-point correlations. So you would have a correlation between 1 and 3, 2 and 3, 1 and 2. And there is what we call a proper 3-point correlation as well, which we do not have in a Gaussian random field, but in anything non-Gaussian, and so on and so forth. Right? Another possible approach at the mean field approximation starts with what is known as the Hubbard-Stratonovich transformation in solid-state physics or statistical physics. And this is a way how you can use a Gaussian identity to replace one theory, strongly coupled, to another theory, weakly coupled. This could be another way to evaluate this interaction term. We don't know this yet. What I wanted to show you is just, we don't need to get stuck, oh dear, don't need to get stuck with the perturbation theory. KFT and its application to cosmology in particular must be the ideal playground for using the mean field approximation. The main problem is at the moment how to find the right average, the right way of averaging this term here. What we have seen so far from this very crude attempt that I've shown you is extremely promising. The whole power spectrum takes 42 seconds to evaluate, nonlinear power spectrum. This is in comparison to 6 months on a supercomputer for a numerical simulation. And of course, we have scaled the number of points along the nonlinear power spectrum such that it does take 42 seconds to honor the fundamental meaning of the number 42. Okay, I wanted to show you this. I hope you are as optimistic as I am looking at these results. I'm not expecting that you are convinced of the whole approach. And this is one possible way, and there should be much better others. But this is an indication that the mean field approach is promising. It's going to the right direction. Okay, need to go. Questions next time. Bye bye.